Hi, welcome to videos on Nyquist plot. In this video, we will see a few more Nyquist plots, how to plot it, and what is the stability of the system. So let us consider the open loop transfer function of the system having a pole at the origin. Of course, so there are two poles on the left hand side of the S-plane, and we have a 0 on the right hand side of the S-plane. So this is the location of 0. We have a pole at the origin and two more poles on the left hand side of the S-plane. So since it has got a pole at the origin, so the Nyquist contour is consisting of actually 4 segments: segment 1, segment 2, this is segment 3, and this is segment 4. So as we usually do it for mapping different segments of Nyquist contour onto GH plane, so we are taking S is equal to j omega for mapping first segment. So upon substituting S by j omega, trying to obtain the magnitude expression, magnitude of this transfer function with S as j omega is given by this particular equation, and the phase of this particular transfer function by replacing S by j omega is given by this expression. As you can see, this is minus 90 degree because of this 1 over S term, and of course because of 2 poles we have minus tan inverse of omega by 4 omega by 2 and minus tan inverse of omega by 3, and we have one more 0 on the right hand side. This is actually tan inverse of omega by minus 1. So this tan inverse of course this is slightly missing it out, tan inverse of omega by minus 1. This omega by minus 1 will be written as 180 minus of tan inverse of omega by 1. So this is a adjustment we are making to eliminate that minus 1 in the denominator of tan inverse of term. So finally the expression becomes the phase expression becomes plus 90 degree minus of tan inverse of omega by 2 minus tan inverse of omega by 3 minus tan inverse of omega. So with this as the phase equation for this particular transfer function for the mapping of first segment. So this is the expression, and of course you can see as the value of omega changes from 0 to infinity, we have the magnitude as when it is 0 the magnitude is infinity, and the S value is or when the omega value is infinite, this magnitude becomes 0. Similarly, the phase varies from plus 90 degree till minus 180 degree. So this is how the phase is varying. And if you can see, the second segment mapping will be a dot at the origin. So this is 0 at magnitude, different angles. Now this will become, so this will be, so this would have been minus 2 theta, because I'm going to have this as r e power j theta. This is actually minus 2 theta. Okay, anyhow that is minus 2 theta, 3 theta. So this is a dot at the origin. Whereas segment 3 will be the mirror image of segment 1. For segment 4, we'll be replacing S by rho e power j phi, where rho is tending to 0 and phi is varying from minus 90, 0 and plus 90 degree. So that is what is given over here. You can see this is the expression. Now this is 100. Now it is S is replaced by rho e power j phi minus 1. And here you can see this S is replaced by so and so, and you can carefully notice here. So as rho tends to infinity, this term will become 0. You end up with minus 1. You can see this is that minus 1, 100 minus 1. Whereas in the denominator I have 2 and 3. This is 2 into 3, and of course rho e power j phi. So please notice that there is a minus 1 here. This is this has to be very carefully considered. So now we end up with, when rho tends to 0, that is the radius of the segment 4 happens to be tending to 0. When this rho tends to 0, the entire magnitude becomes infinite. You can see this minus 1 is now represented by minus 180 degree, and here you can see in the denominator, since I have it as rho e power j phi, the angle will go onto the numerator and will become minus phi. So the overall angle happens to be minus 180 degree minus of phi. Since we know that phi is varying from minus 90 degree, 0 degree and plus 90 degree, substituting this phi as these 3 angles, we end up with the final mapping of segment 4 onto GH plane will be infinite magnitude, the phase is minus 90 degree, minus 180 degree and minus 270 degree. So this is how the mapping of fourth segment onto GH plane looks like for this particular problem. Okay, this is the final Nyquist plot in GH plane. We can notice exactly here, this is for mapping of first segment. So we are starting with the magnitude of infinity at an angle 90 degree. You can see this is infinite magnitude, the phase is 90 degree. And you can see the phase is keep reducing, it will go to 0, it will go to negative, and it will finally end at minus 180 with the magnitude 0. You can see this is the one which is moving here with infinite magnitude, goes to a phase of 0 here with some magnitude. You can see phase is becoming negative and it finally goes to minus 180 degree here. This is the magnitude is 0 and phase is minus 180 degree. This is mapping of first segment starting from infinity at an angle plus 90 degree. It goes down here and then ends at minus 180 with the magnitude 0. And then it is taken over by the second segment. Second segment is a dot at the origin, that's why it stays there. The third segment takes over. The third segment is exactly the mirror image of the first segment. That's why you can see it exactly looks like the mirror of first segment mapping. So it comes down till here. So this is infinite at an angle minus 90 degree. So from here onwards, the segment 4 should take over, because as I said in the previous video, it's like running a relay. The segment 1 has started from here, it ran till here, and segment 2 just passes the baton over there at the origin itself. Now segment 3 is running, it just ended here at infinity at minus 90 degree. From this particular point, the segment 4 should take over. You can see segment 4 is at infinity at an angle minus 90 degree. It's exactly this point. And from here it runs with a magnitude of infinity. It goes, it starts from minus 90 degree, goes to minus 180, and then finally ends at minus 270. This is exactly how it is moving. This is infinity at an angle minus 90 degree. It corresponds to this. Then it is going with the magnitude of infinity. It goes up to minus 180, which is this second phase angle with the same magnitude infinity, and finally goes to minus 270 degree at an angle, at a magnitude of infinity. So you can see the S-plane contour was also a closed path, which is exactly like this. It started here, went till infinity, then came down negative, then went up, and then this is. So since this is also a relay, like, okay, segment 1 runs here, then segment 2 runs the entire semicircle, segment 3 runs till here, and segment 4 runs this very small radius. So likewise, similar type of relay is ran in GH plane. It goes till here, and then second segment is a dot, third segment comes down here, fourth segment again completes the relay by going from infinity at an angle minus 90 degree to infinity at an angle plus 90 degree. So this plus 90 is nothing but minus 270. So plus 90 and minus 270 degrees are same in Nyquist, of course, in the polar plot. So since this minus 1 plus j0 comes inside, if you can see, if you just extend a line here, so this actually encircles this minus 1 plus j0 once in the clockwise direction. That's why n is equal to 1. So as we know that p is equal to 0 in this particular case, because there are no poles on the right hand side, so n is 1, so that becomes 1. So meaning that system is unstable because one pole is there lying to the right hand side of the S-plane. When I say one pole, it is one closed loop pole is lying onto the right hand side of the S-plane. So this way we can say that system is unstable. Actually system is absolutely unstable because whatever the value of this 100, it will be always encircling this at least once in clockwise direction. It says value of n is always 1, irrespective of this, whether it is 100, 1, 10 or 0.1. So it will be always the same. So we'll move on to next plot. So you can see now this is a different transfer function having repeating poles at the origin has got a 0 as well as a pole on the real axis. So this is the segment 1 replacing s by j omega, magnitude and phase equations, fairly simple. And of course this is the overall phase equation So this is minus 180 sound. So this is how the phase is varying. You can see the initial and final phases are both are same, but make sure that, so this actually since you have one is minus, other is plus, this actually dominates because this has got more magnitude. That's why the phase becomes minus 178 and then minus 167, finally goes to minus 180. So since we have for second segment is a dot at the origin, third segment is a mirror image of segment 1, fourth segment you replace s by rho e power j phi, where the value of rho and phi is known to us. Upon doing this, you can carefully observe again you can see the mapping of fourth segment. Again carefully see the mapping of fourth segment. It is 100 into 2. This is because rho is tending to 0, because 2 plus 0 is almost is equal to 2, whereas here it is again 4 plus 0 is like, okay, 4, and but you have it as a rho square e power j 2 phi. So this is what you have. So this will end up with giving a magnitude of infinity and a phase of minus 2 phi. Minus 2 phi is the phase. So let us try to understand, okay, how does this entire plot looks like. So this is the phase and magnitude of segment 1. So okay, segment 1 actually starts like with the magnitude of infinite and phase of minus 180 degree. You can see the phase 1, segment 1 is going with an angle which is in the third quadrant, which is minus 178, minus 167, and finally again reaches minus 180 degree. You can see this is your segment 1. This is segment 1. It has reached here. So this is segment 2 is a dot at the origin. Segment 3 is exactly the mirror image. So it just came here. So now this is the ending point. If you can see, this is the ending point, which is infinity at an angle minus 180. Since minus 180 plus 180 both are same, it is coming here, and then as a value of as the fourth segment starts, so it is having a magnitude infinity. From 180 degree it goes to 135, which is here, and then goes to 0 degree, and then goes to minus 135 degree, and then ends at minus 180 degree. Actually this minus 1 plus j0 is not at all encircled by this contour. If you can see here, this came up to minus 180 and then it is going back here. So this is not actually crossed at all. If you can see, this is a zoomed version of this. This minus 1 plus j0 is not at all encircled by this contour. So n is equal to 0 in this case. So actually it is not at all encircled. The value of n is equal to 0. It looks like it is encircled, but it's actually not crossing here. That's what it is. It's not crossing here. So if you zoom this portion, it looks like this. It looks like this. So since n is equal to 0, p was also 0. You can see there was no poles on the right hand side of the S-plane. So that becomes 0 means there are no poles. There are no closed loop poles lying onto the right hand side of the S-plane, meaning that system is stable. So this way we can able to draw the Nyquist plot for even a complicated transfer function carefully, noting that, okay, here you can one point to observe here is that it goes at minus 180 and then again starts at 180 degree in that second quadrant. So that's why it is not crossing this minus 180 degree line at all. So the system is stable because n is equal to 0, p is also equal to 0. That's why system is stable.